Hi, my name is Adolfo Campos, and I will explain the experiment of the standing wave. First of all, we need to understand what is a standing wave. We can create one by grabbing a string and making a wave happen on it. The wave will travel along the string, but if we put a node right at the end of that string, for example, right here, the wave will get reflected, and the reflected wave will interact with the original wave, and on a critical wavelength, depending on the length of the string, the two waves will appear as the string as a whole will appear as if there was just one wave, which is not moving; it's static on it. That's a standing wave. Here is an example of it. As you can see on this one, this creates this type of wave with one antinode on the center. And here is the formula of length the length of the string is equal to the wavelength of this wave over 2. And it's called a first harmonic. We can still get a second, third, and etc. harmonic. What's important to know is that the number of antinodes define a special value we know as n. For example, on the second harmonic, n will be equal to 2. It will be important later. So the objective of this experiment is to get on a real experiment a standing wave and calculate the linear density of the string using formulas for this standing wave. So here is what we're going to use, these formulas. As you can see, the frequency of the wave can actually is equal to the velocity of. Remember, it's not an actual just one wave; it's two waves interacting, and each one, and then have a velocity. So it's the velocity of those waves over the wavelength, which is equal to the n, which is the number I talked about earlier, times the velocity divided by 2 times the length. This is because we are using these formulas right here, a generalization of these formulas. Here, here, and here. Okay, so, but we can also replace the velocity, as velocity is equal to the square root of the tension divided by the linear density. So therefore, we get this formula right here, which is actually the main formula we're going to use for this experiment, which is the frequency squared is equal to n squared times the tension over 4 times the length of the string squared times its linear density. And as you remember, the linear density is what we're going to try to calculate. So how are we going to do this? We are actually going to use various data points on the same string. And in order to get those data points, we're going to use different tensions and therefore get different frequencies. As its length, its linear density, and the number n, it's the same on all these for all these points. We can actually graph the frequency squared versus the tension and get an estimate of the linear density. So here's how the experiment works. On the left, we have an overview of the experiment. We have a vibrator on the right here. This is what creates the wave. And on the right, we have an image of the actual experiment. The vibrator will be this thing right here, which goes up and down very fast in order to create the standing wave. Here we have the wave, and on the end, there's a pulley system on which the string connects to a mass. This is because this mass will actually create the tension on the string, because the string is not fixed here, it's actually fixed here. So therefore the tension is dependent on the force, the downward force this mass produces on the string. So this force is actually the force of gravity, which is equal to this mass right here times the gravitational acceleration. And this will be equal to the tension of the string. Therefore, what we're going to do is replace this mass with various different values of masses in order to get different data points in order to get our graph. So here is the video of the wave happening. As you can see here, there are 4 antinodes. So therefore, the number n is actually 4, because this is the 4th harmonic. So here is our data represented. Here we have the mass of the string, the total length of the string, and the standing wavelength, as well as the harmonic number, which remember was 4. Here we have 2 different legs because it's important to differentiate them. The first one is the total length of the string, which here on our diagram will be from here, where it's connected to the vibrator, all over here, which is connected to the mass. But the part of the string which is actually making the wave is not the whole string, it's just this part right here. So we need to take that in consideration for our experiments. Theoretically, the linear density will be the same no matter how much string there is. So therefore, for the theoretical, we're going to use the total length. Here's our value, and its uncertainty. The uncertainty was calculated using the formula down below. Here is the formula for the linear density, and for the uncertainty, it's equal to the square of the uncertainty for the mass times its derivative plus the square of the uncertainty of the length times its derivative. The derivative of the mass is 1 over L, and the derivative of the length is minus the mass over the length squared. So replacing this in our formula, we get the formula here down below, and this is what was actually used in order to calculate this uncertainty. Okay, so we have our linear density theoretical. Now we need to get the experimental one. As you can see, here is what I explained, that this part here is actually what creates the tension. So tension is equal to mass times the gravitational acceleration, and its uncertainty is simply the uncertainty of the mass times the gravitational acceleration, as g is only a constant. So here's the values we got. Here are the different tensions we got from the different masses and its respective uncertainties. Now we need to know the square frequency. As remember, the formula uses the square of the frequency. The uncertainty of the square of frequency is actually the absolute value of 2 times the original frequency times its uncertainty. And as we use different tensions, it produces different frequencies. So all the uncertainties will be different. It is reflected on our values right here. As you can see, each value corresponds to a different uncertainty. So we have our y-axis and our x-axis. The frequency squared will be y, and the tension, y, and the tension will be x. So the rest, which is this part here, will be the slope of a linear best fit line, which includes the linear density, as you can see right here. So here is our graph. As you can see, the values do follow a linear path. Not exactly, but it includes their error bars. So here is our value for the slope, which is this number right here, as well as the uncertainty, which was calculated using the uncertainty calculator on the program Python. Okay, so in order to calculate this experimental uncertainty, we need to use the formula for the slope. Here the slope is represented by the letter m. No, and as you remember, the harmonic number n is actually constant. It's 4. So it can be replaced here by 4 squared, which is 16, which cancels this 4 down here, and we get 4 over the length squared times the linear density. So this tells us that linear density is equal to 4 over the length squared times the slope. And we can get this uncertainty using the same formula as we used before, which is the uncertainties times its derivative squared. And we actually can get the 4 outside of this square root, as it's a constant. So here are our both derivatives we got. For the length was minus 2 over the length cube times the slope, and for the slope was minus 1 divided by the length squared times the slope squared. So here is our uncertainty formula. So with the values we got on the graph, which are these two, we can apply both these formulas to get these two uncertainties. As you can see, the uncertainty is actually really low compared to the real value, because it's times 10 to the minus 5. So when compared to the theoretical uncertainty we got earlier, right here, we get a pretty big error of 60%. Now, why is this? This is because the formula we used is not exact. It assumes one thing, that the linear density stays constant no matter the tension it has. But if we have a string, for example this string right here, and we apply a tension to the left side, the string will be actually bigger because the force forces it to get bigger. So therefore, the linear density as its mass didn't change will be lower because it's the same mass over a different length. So therefore, the linear density is actually dependent on the tension. And here are the formulas that describe them. As you can see, it's first of all, it's the linear density we used before is actually equal to an average linear density times the length of the string divided by the length plus a tiny change of length. This tiny change is actually the tension divided by this spring constant of this string. So if we replace this with the original formula we had, which is this one down here, we get this formula right here. And by just replacing and reducing terms, we get this final formula. So as you can see, the tension is not a linear variable compared to the square of frequency. It's actually a squared variable. It's a parabola, not a straight line. So what we're going to do now is, instead of use a best fit line which is linear, we're going to use a best fit line which is parabolic. It's the squared. We're going to use this term right here, which will give us the ideal linear density right here. As you can see, it's very similar. It's actually practically the same to the original formula we used. So the calculations we used before apply here as well. So here's the graph. As you can see, the best fit line is a little bit curved because it's now a parabola. And we get a different number and a different uncertainty. As I said, they are calculated using the same values. So here is the same formula for the uncertainty right here. It's simply the same. Just replace the linear density with the ideal linear density, and the slope with the different slope we got. So here on blue was the previous linear density we got, and now on green is this ideal linear density applying the polynomial slope. So as you can see, they differ quite a lot, and the error is much lower, just 17% compared to our theoretical linear density. So this formula, as it takes into account that the linear density changes with tension, is more exact, and as is this reflected on the results, as we got a closer value to the theoretical one. So therefore, this is the correct formula, and the phenomena of the standing wave and its formulas can be used to calculate linear density to accurate state, around 18% of error. So thanks for watching.